Okay, so let's continue with what we were discussing the other day, the collapse of the inner horizon into space-like singularity. Just so that you remember, I have drawn here again the space-time as it corresponds to the Kerr case. Remember that the limits of predictability are within the, not like this, but like this. The limits of predictability are within this kind of triangle. It's not a triangle, but you understand what I mean. Okay. As soon as you get outside of it, you run into a problem. And the problem is the following. If you start with a well-posed mathematical problem, which means that you start from a Cauchy slice of a space-time with a world line that might start, for instance, over here, you can follow the evolution of this world line up to this point here. I have indicated on this diagram the position of the Schwarzschild event horizon just as a reference point, because it is not present in this diagram, which is a non-perturbed Kerr black hole. But still, it is good to guide your eye. Now, the problem when the world line hits that line, which is, if you remember, the inner horizon, is that we do not know what is going to happen to the observer. It could follow that world line or this one or that one. We don't know that. And that's a big problem because this is not what you expect from a well-posed theory. A well-posed theory, physics, mathematics, allows you to predict the future. And this is not what we have here. We have something different. We cannot predict what is going to happen to the observer. In this diagram, we have the singularity exactly here, r equals 0. So this is the singularity. And because it is Kerr, the singularity looks actually like a ring. So we have that r square plus a square, that's the value of the spin, cosinus square of theta equals 0. And that is also a bit of a problem because in principle what this is telling us is that if we accurately choose phi and theta in a determined way, we can avoid the singularity. We can avoid getting off of our manifold. So we could cross the singularity without leaving our manifold. And that's problematic, to say the least, because in this kind of situations, for instance, you could see yourself you could see yourself in the past, and we don't like these kind of situations. They are very interesting, but we probably our brain is not done to deal with them. And because the singularity r equals 0 over here, we have just made a little bit of room, is a place in space-time, not a moment. In principle, if this was our world line, we could see this singularity if we had, people sitting around it and sending us rays of light like this. We could see a ring of emitters sitting around the singularity like a lighthouse, telling us not to approach it. Now remember that this is a situation that physicists did not like at all when Roger Penrose presented the result. And he himself came up with a conjecture that this is probably not happening in nature. And the reason for that is that from the moment in which the observer crosses the event horizon of the black hole, which is this point over here, up to the moment in which he crosses the inner horizon, which is this other moment here, or place here, that person, when looking over the shoulder, he would see all of the light of the universe up to this point here, which, if you remember, is I plus. So this is a time-like point in the infinite, in the future infinite, because you have an infinite amount of energy density that would cause the singularity to collapse and turn into a well-behaved, so to say, time-like Schwarzschild singularity. And I say well-behaved because we know how to deal with that. It's the end of time. You cannot extend the manifold out of there. There is, by the way, a theorem that proves that, and we are happy. Now, this conjecture that Penrose put forward goes also by the name of the blue sheet, because it corresponds to exactly the contrary situation that we had when an infalling observer was crossing the event horizon. I had the wavelength stretched by an infinite redshift. Now we have an infinite blue shift, after which this phenomenon is named. And this is why they came up with this fancy name, the blue sheet, which has nothing to do with the problem of windows. Other names, other interesting names that have been put forward are, for instance, mass inflation and others. Mass inflation because the mass of the black hole increases exponentially because of the same physical idea. You have an infinite amount of light which has energy, right? And you know that energy and mass are very closely related in relativity. And that's going to, inflate the mass of the black hole. It's going to, the mass of the black hole is to increase exponentially. Contrary to the redshift, close to the event horizon, when we are near the inner horizon, this blue shift destroys everything and leads to the collapse of the inner horizon itself. Now, this is the intuitive description of what happens. However, since the proposition of this conjecture, there has been a lot of work, and in particular, Amos Ori, whose name is associated to this problem, and others, did perturbation analysis of the inner horizon to explore this conjecture. The picture that emerged, which was developed from the mid-90s, is that in fact a segment of the inner horizon, the one close to I+, to this vertex, when we fall into the black hole at a very late time, remains time-like. There is a null singularity there, and it is weak in some sense. And when I say a weak null singularity, I am meaning that you can cross it without being torn apart due to the integral of the forces acting on you, because these are finite or bounded. So we have a weak singularity. Certain curvature components do blow up if you are an observer in the way to falling into the black hole. But if you navigate carefully, you can manage to find finite tidal forces which will allow you to cross the inner horizon. So it looks that Amosori and his collaborators and other people, just citing this one because it's the one that I know, managed to bring back the problem to the table. We do not know what happens beyond the inner horizon. And again, we have a problem, a conceptual problem of a very well-posed theory, which is general relativity, that delivers unpredictable results. Now, this is the picture that emerged from perturbative studies. In the previous video and lecture, if you remember, I mentioned that Dafermos and Luk made in 2017 a mathematical, rigorous study of this problem in full general relativity without perturbations, and a very minimal set of assumptions. They start with any set of initial weak conditions, and the only assumption that they make is that asymptotically, after the collapse, things should look similar to the Kerr case. Now, the solution of Dafermos and Luk confirm the work of Amos Ori in the 90s and actually generalizes it, that the singularity is null. The inner horizon is a null surface. They prove that you can extend the metric continuously through the inner horizon as a C0. C0. I will explain this later in a hand-wavy way. Because the work of Dafermos and Luk is so general and not perturbative, they can study the general solution. They concluded that the inner horizon is weak and null all the way, not just the region close to the vertex. All of the inner horizon, all of this, and of course this, is described by a weak null singularity. So we know that the conjecture of the strong cosmic censorship, blue sheet, or mass inflation, whatever you want to call it, is not valid. You can extend the metric beyond the Cauchy horizon. This horizon here. They proved, and I hope that you understand the implications of what I am saying, they have proven that you can extend the metric beyond that horizon. It is not clear, however, what is going to happen after that, and how to further develop the theory, which makes this, in my opinion, one of the most interesting and open questions of theoretical physics and mathematics right now. So you see, it's not that we are facing the problem of the singularity not being contained in our manifold. It's a totally different problem. Dafermos and Luk, they prove that when you cross the inner horizon, any world line is possible. There is no preference for this or the other one. General relativity has a range of predictability before reaching the singularity. Why is this a problem? Well, this is a problem because the Kerr solution, the one that we are studying here, the exact Kerr geometry, the one which comes out of the solution corresponds to a geometry which has been there forever. It wasn't generated by initial conditions, by a collapsing gaseous cloud or whatever. And in that picture, the picture that we are dealing with, you get the ring singularity and the other features we have discussed. However, there is no guarantee that these things exist as the result of a dynamical collapse. We do not know what happens after the horizon because the theory doesn't tell you. So mathematically, the answer is correct, but physically it is probably not motivated. As usual, and as I have been saying many times to the students, you need to keep your feet on the ground. We do not know if there is a singularity in the inside. All we know is that we don't know it. We cannot predict. The breaking of causality at the inner horizon is equivalent to saying that the system is not globally hyperbolic. Remember, only within this triangle we can predict the dynamical evolution of a world line from initial data. And what does this mean? This means that outside of the triangle, we do not have a physical space-time. In the physical spacetime, the perturbed one, the inner horizon is not a Schwarzschild singularity. It turns out to be a weak null singularity. Some curvature components do blow up there, but the metric can be extended as a C0. So the metric can be extended as a C0. This is, well, I would have to explain a couple of things, and I will probably do that because if you remember well, this is meant to be a kind of motivation introductory course to a set of lectures that I intend or would like to be given about differential topology and geometry, starting with topology and metric spaces to motivate the geometry. But anyway, CK, when you have a CK, this means K differentiable. When K equals 0, it means that it is continuous. Okay, and this is what Dafermos and Luk proved. They explain that because of having an n-smooth manifold, you cannot apply Einstein's equations there. So when you cross that inner horizon, when you cross this inner horizon here, you have a problem over here. You have a manifold which is anything but smooth, so that you cannot apply Einstein's equations there. This is why they work with LP spaces, which are spaces of functions f such that f to the power of p is integrable. If you want to know what to study in terms of mathematics for general relativity and this problem, you should take Ringström's book, Hans book, which is called let me remember, the Cauchy problem in general relativity. Yes, general relativity, which is yes, this is lectures in mathematics and physics, band. Let me check it. The notes is band 6. So what I am saying here is that you have a weak null singularity, and remember you can cross it because the forces acting on you are finite or bounded. When we talk about strong singularities, we mean that the metric becomes infinite, and mathematically you cannot attach another universe in the future of the singularity in such a way that it connects continuously to the previous one. And you can prove that. In the case of a weak singularity, the metric is finite and continuous, although some components of the curvature become infinite. This means that the metric can be extended as a C0 metric. You can make an extension of the metric and extend the manifold. And note that I am not saying unique here. You can extend it, but not in a unique way, the metric as a C0 metric. And by the way, the work of Dafermos and Luk is completely classical, which is fine, because we are very far away from any kind of distance at which quantum effects should be important. So this is a classical problem. The inner horizon over here, depending on the mass of the black hole, could be at kilometers or even millions of kilometers from the singularity, r equals 0. Quantum effects do not play a role here. We're testing our theory in a classical regime where we expect it to work, and it does not. And just to finish with, because some students asked me, super extremal Kerr, so super extremal Kerr, which has a spin, larger than m, will have no event horizon, and the conformal diagram looks as boring as this one. Here we have flat space, and this is the singularity. On the left, we have the singularity and no event horizon to protect us from it. De facto, there is no black hole, and there is a naked singularity, of course in violation of both strong and weak censorship. The diagram for the extremal, not superextremal, but just the extremal case, in which A is equals to M, looks different. There is an event horizon. The time-like singularity is hidden behind it, and weak censorship holds. Only the strong one is violated.